Hello, and welcome to the last video in the alum synthesis video series. Looking at my saturated alum solution, the first thing you probably notice is that a little under half of the saturated alum solution has evaporated. In this close-up picture, you can more clearly see 6 of the 8 alum crystals in the vial. The largest central one is approximately 1 centimeter long, 4 millimeters tall, and 4 millimeters wide. The two other medium-sized crystals are about 5 millimeters tall and 3 millimeters long and wide each. The small ones are less than 1 cubic millimeter large. Some of the small crystals are impossible to capture clearly on camera, but in this next picture, I did manage to capture the two largest small crystals. All of the crystals are clear octahedrons with flat smooth faces and sharp edges and corners. I believe that the reason several small crystals are forming is because the vial accidentally tipped over since the last video. This disturbed the stationary positions of the alum crystals. Recall from the last video that minimal vibrational disturbances are an important environmental factor to maintain, as they decrease the number of nucleation sites, which increases the chances of larger crystals forming. Besides that, the environmental conditions in my room have been suitable for slow evaporation crystallization. Humidity is normal at around 35 to 45%, and temperature is kept at a cool 67 to 68 degrees Fahrenheit in my dorm. Now, you may be asking yourself, how could one make a single large high-quality alum crystal as opposed to several smaller ones? Well, the answer to this question is you have to limit the nucleation sites to one. If there is only one nucleation site, then the alum molecules in solution can only aggregate at that one site. This would form one single large crystal. This can be achieved by suspending one of the seed alum crystals we have with the nylon string in a saturated alum solution. Nylon is used because it is smooth, and this minimizes the chance of crystals forming on the string. This way, alum molecules in solution are able to aggregate on all faces of the alum crystal, enabling it to grow larger. If crystals do begin to form in other places, they need to be removed. Note: the suspended alum crystal has to be completely submerged in saturated alum solution at all times. In this new procedure, the same slow evaporation crystallization technique would be used. Now I'm going to introduce a concept called Bragg's law. In simple terms, the law is used to help us identify unknown crystal minerals through X-ray diffraction. Here is the equation on the screen. N lambda equals 2d sine theta, where n, an integer, is the order of reflection, lambda is the wavelength of the incident X-rays, d is the interplanar spacing, or d-spacing of the crystal, and theta is the angle of incidence. Before I go too deep into this, let's step back a bit. Recall that the atoms in a crystal form a crystal lattice. This means that the atoms are arranged in a very specific periodic way. This periodicity of the atomic planes affects how crystals interact with light, in this case X-rays. To be a bit more specific, it is the spacing between these planes of atoms, or the d-spacings, and the angles at which these planes intersect that determine the positions of atoms in the crystal. This is obviously very difficult to observe with the human eye, so we use X-rays to try and help us pinpoint these d-spacings and angles. As you can see from this experiment's X-ray diffraction graph, the light intensity is plotted against the angle 2 theta. Notice that there are several sharp peaks on this graph. It is at these peaks where the wavelengths of scattered X-rays interfere constructively or increase the intensity of the light reflected. This only occurs when the distance traveled by these wavelengths are integer multiples of the wavelength, allowing the light beams to reflect at the exact same angle. To connect it back to d-spacing, it is at these peaks where the distance between the parallel planes of atoms allows for constructive interference of the light beams to occur. Now, you may be wondering why all of this is important. Well, each mineral has its own unique set of d-spacings, so identifying the d-spacings of an unknown mineral and comparing it with the identified d-spacings of other minerals, we are able to discover the identity of an unknown crystal. Here's how we can calculate a d-spacing of a crystal. From the graph, we know the lambda value to be 0.15418 nanometers. We also know the 2 theta values for all the peaks. Focusing on the highest peak, we can see that the 2 theta equals approximately 20.7 degrees. This leaves d as the only variable left in Bragg's law equation. By dividing both sides of the Bragg's law equation by 2 sine theta, I get d equals n lambda over 2 sine theta. Now, the graph only gives 2 theta values, so we need to divide 2 theta by 2 to give us theta. This gives us the final equation d equals n lambda divided by 2 sine 2 theta over 2. Plugging in the known values, I calculate the d-spacing to be 0.429 nanometers at the highest peak of the graph. Well, that brings an end to the alum synthesis video series. I hope you enjoyed, and once again, thanks for watching.